let us now look at the case when there is some friction force. So this is called the damped oscillations. So, for example, if your motion happens in the air, then of course there is some air resistance, and the amplitude of the motion is going to decrease as time goes by. And so we're going to model it by introducing a new term into the equation, right? So the resistance means that the resistance is its direction is the opposite of the acceleration. That's why the minus sign. And it is proportional to the speed of the object. So basically, the logic here is that the faster it is moving, the higher is the resistance. And hence, the equation for the damped oscillation is like this. Right? So here, this gamma is the damping constant. So notice that the characteristic equation has all positive coefficients, right? So all these numbers, m is positive, damping constant is positive, spring constant is positive. Well, all alternatively, we have the displacement and the gravitational acceleration. Still, everything is positive. So what I needed to figure out are two things. So by discussing now, yeah, I cannot meet you in person right now, but I suggest that you try to answer these questions. You pause the lecture, you answer these questions for yourself, and then you listen to my explanation. And so, what are the units of gamma, and what does it mean for the characteristic equation to have all the positive coefficients? And so, let me explain the units of gamma first. If we have our equation mu double prime plus gamma u prime plus whatever. The important observation here is that since we are adding some quantities, it means that their units must be the same. We cannot add, say, meters and kilograms. That doesn't make sense, right? So we can only multiply meters and kilograms. So what are the units of mass? So the units of mass are kilograms. The units of the u double prime, which is acceleration, are meters per second square. Plus, so we have our gamma, and the units of u prime is the speed. So the units of the speed are meters per second. Now for the whole thing to match, gamma has to be measured in kilograms per second, right? So, and this is how we can figure out that the damping constant is measured in kilograms per second. So that's the answer to the first question, right? So the damping constant, gamma, is measured in kilogram per second. And so that's a funny thing. So it has the same. So imagine that you are losing weight, or I don't know, gaining weight. So the rate of change is measured in kilograms per second. So same here. Same units. So another very, very important observation here is that all the coefficients here are positive, right? And so the characteristic equation basically has the following form. So r square plus a r plus b is 0, where a and b are positive. But I hope you still remember from secondary school that b is the product of the roots of the characteristic equation, and a is minus the sum of the roots. So r1 plus r2 is minus a. Right? So if the product of the two roots is positive, it means that the roots are either positive or negative. Right? But since the sum of the two roots is negative, it means that they cannot be both positive, so both have to be negative, right? So in other words, the coefficients of the characteristic equation are 0 if and only if both roots are negative. And since both roots are negative, the general solution of our equation, it has to do with e to the power r1t and r2t. So as t goes to infinity, this term approaches 0, and this is actually consistent with the physical meaning here, right? So because we have a frequency force, it means that eventually oscillations are decaying, and everything is just going to converge to the equilibrium, to no movement at all. Okay, so here is the discriminant of the characteristic equation, and essentially there are three cases. If the discriminant is positive, it means that there are two distinct real roots of the characteristic equation, right? And in this case, we say that the system is overdamped. Right? So if the discriminant is 0, then we say that we have one repeated root, so then the system is critically damped. And if the discriminant is negative, then the damping is small, so we do not usually call it underdamped or anything, so we just say small damping. And then in this case, when the discriminant is negative, it is when we are going to have some oscillations. And so let me show you some very simple animation in Desmos calculator. And so this is how L affects it. So here it doesn't really distinguish between, it doesn't feel the damping, but if we change the damping constant, so the bigger it becomes, so damping becomes bigger, so we have oscillations that are decaying faster, and then at some point oscillations disappear. And at this point, at some point, the discriminant of our characteristic equation becomes 0. I think it's about that point. So here there are very, very quickly decaying oscillations, and here we don't have oscillations at all. And then, if the damping becomes larger and larger, then it just means that we don't have oscillations, and rather we just release our string or whatever, and then it slowly goes back to its equilibrium position. All right. Anyway, you can play with this at home. All right. So let's very quickly go through these cases. So the first is overdamped system. Then we have two real roots, and an arbitrary solution is a combination of exponential functions with a negative exponent. And of course, it very quickly goes to 0. Right? And a little problem for you to try to do it at home and discuss online is to solve the initial value problem of this characteristic equation, of this differential equation. So here is a critically damped system. So the graph, the plot of the function u of t versus t is very, very similar. You can't really tell whether it is critically damped system or overdamped system. Doesn't matter. And again, I suggest that you try to solve the initial value problem. Well, and the most interesting case is, of course, small damping. If the damping is small, then the characteristic equation has two complex roots. So notice that here, the whatever is inside the square root, this number is negative. And the square root of negative number, it contains an imaginary unit. All right, so here is the general solution. And again, alternatively, we can write it down using this phase and frequency and amplitude. We can write it differently. So if you try to plot it, if you try to plot the function u of t versus t, so let me just again say that this is the axis is u, and this axis is t, and these two curves here, they are plus and minus are e to the minus gamma t over 2m. All right, let us do a word problem. So the trick is here to somehow extract the values of the constants from the words. So here we have 25 kg, 8 centimeters, 17.5 Newton, whatever, 1 meters per second, 10 centimeters. So all these numbers, they're going to become some parameters in our differential equation. And so the first thing to do is to convert centimeters to meters, and this additional 10 centimeters become the initial value. So then, what is the damping constant? So to say that viscous resistance of 17.5 when the mass has a velocity of 1 meters per second. So this really just means that the gamma here is the ratio of the two. Right? So that's our damping constant. And then we just need to put it all together into the equation. Right? So here is the initial value problem. These are our specific numbers. So that's gamma, that's m, that's gravitational acceleration, that's the initial displacement. All right, so the characteristic equation has a negative discriminant. So we can find the roots of the characteristic equation. Square root of 441 is apparently 21, I guess. So over 2 we get 10.5. Yeah, and these are the two roots of the characteristic equation. Right? So the real part is minus 3.5. Because we are dealing with oscillation problems, the real part is always going to be negative. Right? Because then later the real part goes into the exponent, and we are going to it has to be negative so that oscillations are truly decreasing. And the imaginary part goes into the sine and cosine, right? So that's the general solution. It doesn't matter how we write it down. So either way, so here the two parameters are C1 and C2. In the alternative form, so the two parameters are R and delta. So let us use the C1 and C2 form here. Right? So then we can use the given data to find C1 and C2. Right? So C1 is 0.1, and then we just substitute it, and then we can find C2. C2 happens to be 1 over 30, whatever, and that's the final answer. Right? So this is the formula for U of t. One more thing that I wanted to look at is notice that the frequency of the damped oscillations is smaller than the frequency of the undamped oscillations, right? So if you say take this distance, that's half the period, it is a bit smaller than the half period of the corresponding undamped oscillation. So the corresponding undamped oscillation, meaning that the term with u is the same, but the term with u prime, which represents damping, is gone. Okay, so let's recap. So this is our equation. Right? So damped oscillations happen when the discriminant is negative. So if the discriminant is non-negative, then it means that there is no oscillation at all. So we have either critical damping or over-damping, but there is no oscillation. So the word oscillation means that we really have to have a negative discriminant, right? But then the quasi-frequency, so remember that if you have a usual oscillation, then the frequency is the coefficient at t in sine and cosine. So here we also have sine and cosine, so why don't we call it also a frequency? But since it is not a true oscillation, we use the word quasi-frequency. So notice that the difference of quasi-frequency and just the frequency is that if we didn't have damping, then we wouldn't have this term. And this term is positive, so we are subtracting it. The whole thing becomes smaller, so meaning that the quasi-frequency is smaller than the usual frequency, and the usual frequency will be 1/2 square root of 4g over L. Yeah, so remember that the formula for the frequency, we can actually cancel, so it's square root of g over L. So that's the formula from the beginning of today's lecture. Right, so the quasi-frequency is smaller than the normal frequency, and the quasi-period, which is the reciprocal, is of course going